Welcome to the chapter 2, part 7 video. This is solving equations in one variable. So some of this will be review, but we're also going to apply this to the functions that we've been looking at. So what we're going to do, we're going to solve rational equations. Remember, rational means fractions, so that's equations that have fractions. And when we do that, we're going to have to check for extraneous solutions, and then we're going to apply it. And why do we care about this? Applications involving rational functions as models often require that an equation involving the model be solved, and we have to be extra careful, especially when we have fractions that we are not dividing by zero. So that's where the extraneous solutions come in. So what is an extraneous solution? Well, an extraneous solution, extra, means that it doesn't work. Okay, we solve and we get a solution that is extra. Now, what makes it extra? Almost always, it's because when we use that solution, we would have to divide by zero in order to get equal sides on the equation, and we can't divide by zero. The other way that we can have an extraneous solution is multiplying by zero on both sides of the equation, which we also can't do, right? So the multiplication property of equality means that I can multiply both sides of the equation by any number except for zero. So in both of these cases, our extraneous solution comes from when we have x equal to a number that would give us a zero that we're either multiplying or dividing by. Okay, so when we multiply or divide, formally, I'll read this. When we multiply or divide an equation by an expression containing variables, the resulting equation may have solutions that are not solutions of the original equation. These are extraneous solutions. For this reason, we must check each solution of the resulting equation in the original equation. So that just means when we get x, we substitute it back in to check it. So let's look at an example. Solve x plus 1 over x minus 3 equals 1. Okay, so we have an equation. There's only one variable. Our variable here is x. So that means to solve this, we need to solve for x. So the first thing that we would do in order to not have to deal with fractions is to multiply everything by our LCD. Our LCD in this case is x minus 3, right? If I look at all my denominators, I have 1, x minus 3, and 1. So our LCD is x minus 3. So I'm going to multiply everything by x minus 3 over 1 to every term within the equation. That's multiplying it on both sides of the equal sign. Now, by this step, when I multiply by x minus 3, mentally, you can make a note that this means that x cannot be 3. Remember, this also came from a denominator. So our denominator also gives us that x cannot be 3. So that's an example of what we would want to make sure when we get our solutions. X equals 3 would be extraneous. I don't know if that will be a solution, but if it is, it would be extraneous. So let's go ahead and do the multiplication. So we have x times x minus 3 plus x minus 3 over x minus 3 cancels out. I'll write it out though. Equals 1 times x minus 3. So this is going to reduce to just 1. So we have x squared minus 3x plus 1 equals x minus 3. Because of that squared, I know that I want to set this equal to 0. Minus x plus 3 minus x plus 3. X squared minus 4x plus 4 equals 0. Two numbers that multiply to 4 and add to negative 4 are negative 2 and negative 2. So we get x minus 2 times x minus 2 equals 0. Our zero product property, or our zero factor property, says that x minus 2 equals 0 or x equals 2. A lot of us like to skip this step. That's absolutely okay. As long as you understand why the sign switches, I don't need to see that step. So we have x equals 2 or 2, which just means that x equals 2. Notice our extraneous solution was 3, so we should be fine. But how do I check my solutions to make sure that it works? I'm going to substitute that back into the original equation. X plus 1 over x minus 3 equals 1. So if x is 2, that's 2 plus 1 over 2 minus 3. And we're hoping that equals 1. 2 plus 2 minus 3 is -1. 2 minus 1 equals, whoops, 1. 1 equals 1. Yes. So we know that x equals 2 works. Notice the solution that I got here, 1 equals 1, is not my value for x. That just tells me this is true. So x equals 2 worked. The number that I substituted in is the value that I was testing. Okay, this value at the end, 1 equals 1, that has nothing to do with the value of x. Be careful of that. I see it all the time. If you get a statement and you end up with something like 7 equals 7, that doesn't mean that your x value is 7. Your x value is whatever you substituted in. Okay? Let's take a look at our next example. So again, we're solving this. It has a fraction, so we are going to need to double check our solutions. Right away, I'm going to write that x cannot equal 0 because I see that x is in the denominator. And then to solve this equation, I don't want to deal with fractions, so we're going to multiply by the LCD. That is x, because our other denominators are just 1. So multiplying everything by x, distribute to every term, x squared plus the x's cancel out. So I'm going to skip that step. We don't need to do that step every time. Although if it helps you visualize what's happening when you're distributing the x, absolutely feel free to write that step out. Equals 3x. I've got that squared, tells me to set it equal to 0, so I'll subtract the 3x from both sides. Notice I don't have a like term to subtract it from on the left side. So that's going to be x squared minus 3x plus 2 equals 0. Now the reason I said notice that there's no like term is because sometimes you're tempted to say 2 minus 3 is -1, but those are not like terms. So be careful of that. Okay, continuing on to factor this, two numbers that multiply to 2 and add to -3 are 2 and 1. They both have to be negative. So this is x minus 2 times x minus, no, that's right, equals 0. I'm just going to double check. I foiled it. It works. 0 product property says then x equals 2 and x equals 1. Okay, so that tells me I need to check those into my original equation. They aren't 0, so it should work. Okay, but that's the whole point of extraneous solutions. We have to check to make sure that they work. So let's test first x equals 2. So we say 2 plus 2 over 2, does it equal 3? 2 plus 1 equals 3, yes. So x equal 2 works. Then we test our second one. Let's test x equals 1. So that's 1 plus 2 over 1 equals 3. 1 plus 2 equals 3. It works. So x equals 1 works. That means we have two values for x. 1 and 2 both work. Okay. Let's take a look at our next one. So this time we have more than one denominator, so we're going to have to do a little bit more work to find our LCD. So I have x minus 3, I have x minus 1. This is a quadratic, so I'm going to see if I can factor it. Two numbers that multiply to 3 and add to -4 are -3 and -1. That works out nicely because that matches our other two denominators. So to find the LCD, I look at my denominators and I build my LCD by adding a factor of each denominator. So I need a factor of x minus 3 for the first denominator. I need a factor of x minus 1 for the second denominator. For the third denominator here, I need a factor of x minus 3. I've already got it. And I need a factor of x minus 1. I've already got it. So my LCD is x minus 3 times x minus 1. Okay, so what we're doing is I just created an expression, an LCD, that has each of these factors. I need it to contain the first denominator, contain the second denominator, and contain the third denominator. But since the first and third denominator share that factor of x minus 3, I don't have to list it twice. I would have to list it twice if my second denominator had 2 factors of x minus 3. Then I would need another factor of x minus 3. If you have questions on LCD, we'll be able to have a little bit of practice, but if you really want a good in-depth review, set up some office hours and we can go through that together. Okay, so I've got my LCD. I want to multiply everything by my LCD. So I'm going to rewrite this here. X minus 3 plus 2 divided by x minus 1 equals 2 divided by the quantity of x minus 3 times the quantity of x minus 1, multiplying by x minus 3 times x minus 1. And I'm doing it to each term, so I'm just going to write this above each term. And the reason I did that, so that represents my distributing. I can say the x minus 3's will cancel out. 1 times x minus 1 is x minus 1. Plus, the x minus 1's cancel out, so I have 2 times x minus 3 from my second term equals, the x minus 3's cancel out, the x minus 1's also cancel out, so all I'm left with are 2. Now by this step, after I multiply by the LCD, I should not have any denominators left. So if you have a denominator left, that means you had the wrong LCD. Now, that doesn't mean you have to go back and start over. It just means you're going to multiply again by the new LCD. Okay, so it just means that you were missing a factor from your LCD before, but this question isn't asking what the LCD was. So you don't have to start back over at the original LCD. Just pretend this is a new problem, find the LCD and multiply it out. And you want to do that until there's no denominators left. And then we're going to treat this just like our last problem. We need to solve for x, so I'm going to distribute that too. X minus 1 plus 2x minus 6 equals 2. I only have first degree. I don't have any x squareds. So I want to get x on one side and the numbers on another side. So that gives me 3x minus 7 equals 2 plus 7. 3x equals 9 divided by 3. X equals 3. Now, if we look back at our original denominators, I should have some restrictions in my domain. Specifically, x cannot be 3 and x cannot be 1. So what does it mean that I got x equals 3, but also that x cannot be 3? Let's try substituting x equals 3 into our equation. 1 divided by 3 minus 3 plus 2 times 3 divided by 3 minus 1 equals 2 divided by, always into the original. So it's going to be 3 squared minus 4 times 3 plus 3. So I have 1 divided by 0. There's our problem. Plus 6 divided by 2 equals 2 divided by 9 minus 12 plus 3. 1 divided by 0 plus 3 equals 2 divided by 0. So notice I have this divided by 0 on both sides of the equal sign. That's why we get 3 as a solution, because it happened on both sides. However, that is undefined. And that is why x equals 3 does not work. So our only solution doesn't work. Then what is our solution? The answer to this question would be no solution. There is no number that makes this statement true. The other way to write that is the empty set. It's the set with no numbers in it. So it's the set of solutions that is empty. It's the empty set. Okay. So let's see if we can apply this. So we saw that when we're solving equations that have fractions in them, sometimes we get answers and they all work. Sometimes we get answers and none of them work. We can have something in between where some of the answers work. So let's try finding the dimensions of a rectangle with a minimum perimeter. So we want to minimize the perimeter if its area is 300 square meters. So we want to find the least perimeter, the smallest or the minimum perimeter. Okay, so let's start by drawing a rectangle. We know that the area of this rectangle is 300 square meters. How do we find its perimeter? Well, let's start by labeling our rectangle. Let's call one of these sides X. And it doesn't matter if that's the smaller side or the larger side. This rectangle could be a square for all we know, right? I'm just gonna call one of the sides X. Well, the area is length times width. So if one of those is X, 300 equals X times whatever the other one is, the width. So that means the width equals, divide by X, 300 over X. So now I have both sides labeled, and we can write this in terms of a single variable. I don't really need W anymore, right? So to find the perimeter, I start on one corner and I work my way all the way around. So there's X plus 300 over X plus X plus 300 over X. If you were wondering where the formula from perimeter comes from, 2 times length plus 2 times width, it's because you go around the whole thing, which is 2 of the lengths and 2 of the widths. So we have this is 2x plus 600 over x, right? They have a common denominator, so I add the numerators. That is my perimeter. Okay, but I want to minimize this. So whatever the perimeter is, I want to find the smallest value of the perimeter. Okay, so how do we optimize this function? Well, we want to find a minimum. So that sounds like something we've done before. And we have a function that has a reciprocal function in it, but it also has a 2x. So it's a transformation of a reciprocal function, right? So we're pulling together a lot of different concepts we've had. Now, we should be able to recognize that because this contains the reciprocal function, this is a rational function. And so it's going to have an asymptote, a vertical asymptote at x equals 0, right? So we can kind of picture this. It's going to have a vertical asymptote at x equals 0. The quotient here is going to be a whole number, right? So it's probably got a horizontal asymptote somewhere, okay? Now, if I look at this as a quotient itself, we can say that this is the quotient and this is the remainder. So this is actually an oblique asymptote. And the oblique asymptote to x looks like a line through the origin with a slope of 2. So those are what my asymptotes look like, okay? The difference between this function and one of the functions that we were graphing in our worksheet a few classes ago, when we were graphing the ones from our worksheet, it was plus just a number, right? Plus 4 or something. And so we ended up with our horizontal asymptote at 4 in that example. So whatever the quotient is, the whole part here, that's not the fraction, which would be our remainder if we look at this as a division statement, right? That is our horizontal asymptote. If it has an x, it's oblique, meaning it's not a horizontal line, but it's a line that has a slope, okay? A non-zero slope. So if I'm looking at this, the graph is going to look something like this if it's trapped between those asymptotes, right? So I have an idea of what the graph should look like. If I'm minimizing this, x is a distance, so it has to be positive. I'm expecting it to be here. But how do we find that value? Well, that's where our graphing calculator comes in. So let me switch over to the calculator and we'll go through those steps together. Okay, so within the calculator, I typed the function, right? This is the perimeter function. And I want to find the minimum of this. So I want to graph this to see where my minimum is. So I'm going to start with my standard view, zoom, standard. But remember, the asymptotes were between x equals 0 and 2x. So I'm expecting the graph to do something like this. and I don't see anything like that. So what we can do is zoom out. So this is a new thing that I'm showing you. Probably most of you have used this before, but to zoom out, we're just gonna go into zoom menu. Option 3 is zoom out. But the key here is that you have to hit enter in order for it to zoom out, because it's asking you, where do you want the center of your screen when you zoom out to be? So because this is a hyperbola, I'm gonna just center it around the origin. I'm gonna leave it at 0, 0 and hit enter, and then it will zoom out. I still don't see anything, so I'm gonna zoom out again by hitting enter again. And now I see the function, and it looks like what I was expecting. So I'm pretty sure we typed it in correctly and everything. Okay, notice if we were to draw an asymptote along these, along the curves here, the equation of that line would be y equals 2x. Okay, that's what it means to have an oblique asymptote. It's not horizontal or vertical, it's kind of crooked. And it doesn't have to be a line, it could be a parabola, it could be, we saw some examples of non-linear oblique or slant asymptotes. Okay, but that's not what we're interested in. We're interested in the minimum. Now, x is a distance, right? It was the side of our rectangle. So x has to be positive. So we're only interested in quadrant 1. All of these are extraneous by the idea of that this is an application question. Not because it wouldn't work in our equation necessarily, but within the context of the equation, having a negative length of a rectangle doesn't make sense. So we want this point here. So to find this, we're gonna go second, calculate the minimum, that's number 3. And I want it to be between these values. Okay, so I'm gonna use my spider. First question, left bound, so I'm gonna go to the left of that minimum point and hit enter. Right bound, go over until I'm definitely 100% sure that I'm to the right of that minimum point and hit enter, and then enter one more time. It's better to be a little bit farther away than to just try to get as close as you can to the minimum point, because then if you aren't to the right or to the left, depending on which bound you're looking for, that will cause trouble. That'll give you error messages, or it will more likely just give you the wrong answer. So then I hit enter. That's the point that we expected. Let me erase this so we can see it a little better. Okay, that's the point that we expected, the minimum there. And it's telling you x equals 17.32. And in this class, we said 3 decimal places, so 0.321. Oops, let's switch colors. 0.321. And in that case, then y, which is our perimeter, will be 69.282. Okay, so let's go look at that within the context of the problem. So we said that this point, we found the coordinates to be 17.321, comma, 69.282. X is the side of our square, or our rectangle rather. This is the side of rectangle. And this is our y value, which is the perimeter. So the question is, find the least perimeter. It's not asking for the sides of the square, or the rectangle rather. Sorry, I keep calling the square. It's not asking for the sides of the rectangle, it's asking for the perimeter. And so the least perimeter is 69.282. Our perimeter is in units, not units squared. Our units were meters, so this is in meters. And unless otherwise specified, we're always rounding to 3 decimal places in this class. So unless it says round to 1 decimal place or 2 decimal places or whole numbers, always round to 3 decimal places when you're doing your computations. Okay, this is the end of the section. Okay, so what I want you to do is look back through the examples that we did and see if you can redo them on your own. Okay, you don't have to submit a PDF or anything, but make sure that you can reproduce those steps. okay? Some of them are a little bit familiar from algebra, but a lot of them are new, this idea of extraneous solutions and applying that to rational functions, okay? And then this application one, see if you can go back and recreate the equation for the perimeter. That's kind of the tricky part for this, is creating the equation for the perimeter and then understanding what it means to minimize it. Okay, so go back and make sure that those make sense. Not just yes, 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 I can follow along with you, but could you create those steps on your own as well? Okay, and then we will do some practice in class together.